jeden Bitcoin, 2 Bitcoin, to działa. Okay, so thank you to the person who is not speaking Polish, because otherwise it would be weird, me speaking to you when we all talking Polish. I'm Michael, and I work as a senior engineer at Tuplux. I'm someone who I guess you could call polyglot programmer. I like to play with different programming languages, but for the last year, I have quite narrow focus on working with Solidity. It's a language in which you create smart contracts on Ethereum platform, on Ethereum blockchain. But we'll only skim through that topic, and I would like to give you like high-level understanding of how blockchain works and what it is exactly. I'm not going to talk about cryptocurrencies at all. So the agenda for this talk, which I hope will take less than 30 minutes, is what is a blockchain, how the hash function works. That will give us some background required to understand the quasi-live coding of building your own blockchain. I'm saying quasi because I've recorded a video. It will take less time that way. Then I will talk a little bit about Ethereum and how we build decentralized applications. The topic of the talk is how your JavaScript skills apply in blockchain space. And it's that topic, not other, because you have a certain edge as a JavaScript programmer, because a lot of the ecosystems, and Ethereum ecosystem especially, is really friendly for JavaScript developers. A lot of tooling is written in JavaScript and is meant to use through NPM, for example. So the first feature, it's basically an immutable data structure, but not like the one in immutable JS. You can't change it, and it's by design. It's open and decentralized, maintained by the peer-to-peer network. That part we won't code today. But you can imagine that anyone can join the network. You don't need any permission to do that. And it has a certain financial incentive for people to participate in the network. But first of all, that's SHA-256 function, which accepts arbitrary number of bytes and arbitrary data, and always produces 32 bits signature of that data. If you change any byte, it will entirely change the output. We call it the randomness, but for each input, it's going to give you the same output each time, but it's really hard to predict, and that's the feature of whether the particular hash function is safe. It will give you totally different output, which cannot be easily guessed. So to find out, you have to basically calculate this hash. And it gives foundation for how the proof of work mining works. And we will implement that in a moment. There is no real difference when it comes to size of that data. It's any set of bytes you can feed into the function. Okay, so proof of work. You probably heard, unless you live under the rock, about cryptocurrencies and miners that make your graphic cards really expensive. And they use them to calculate hashes. In case of Bitcoin, they calculate this SHA-256 hash. And as I said, there is no better way to find the particular hash than to just try it. So they calculate a lot of hashes to find a hash that commits to certain criteria. What are those criteria? You will see in the code, but it basically protects from spam and DDoS, because otherwise it would be really easy to create a new transaction and flood the network with some spam, basically. And that would make the blockchain, which contains all of those transactions, really bloated. So that's one thing and one issue that is solved by proof of work. There is a cryptographic puzzle, like I said before. So we have a block. This block will contain many different information. Some of them are the list of transactions or any arbitrary data, a timestamp, and a nonce. The nonce is, the name nonce is coming from number only used once. And miners increment that nonce. It's an integer in most cases. They increment the integer and calculate the hash of the entire block. They then increment the integer, the nonce, and they calculate the hash. And they will do that as long as they find the nonce that will produce a hash that meets certain criteria. In many different implementations, this criteria is that the numeric value of the hash computed by incrementing the nonce is less than the current target of the blockchain. So there is a target which aims to be number smaller and smaller and smaller. This makes it harder to find smaller and smaller and smaller hash. I'm saying smaller because we will see that the number of zeros is greater and greater. So those hashes will have certain number of zeros at the beginning. It's really hard to find the solution. It's really easy to increment the difficulty, and it takes tremendous computing power to find it, and there is no better way than try every option. You can start from we will start from 0. You can start from 1,000 and increment from 1,000, but there is no guarantee that the nonce you are looking for is not from 0 to 1,000. So you basically start from 0. And everyone, after mining a new block, so when there's a new puzzle and a new transaction pool to be included into the block, everyone on the world that participating in the network are starting solving this puzzle. And their powerful graphic cards and dedicated devices like ASCII miners are doing only that one thing, calculates those hashes. Really cool feature is that it's super easy to validate. Because to validate, you just only have to compute the one hash. You just take the block, you just take the solution proposed by the miner and calculate only once. And then you know whether the solution is correct or not. So really easy to validate, really hard to find the solution. Okay, and now I would like you go through the implementation. Simple implementation in TypeScript. I'm not writing blockchains in TypeScript on a daily basis, but I hope this will give you some idea of how this stuff works. So our block is going to be rather simple. It will have an index, previous hash, timestamp at which the block has been created, and some arbitrary data. It can be a string, it can be list of transactions, usually it's list of transactions. Then we take informations about the block that doesn't change. Like we won't take a nonce in this case, but everything else. There are a few ways to calculate this hash in JavaScript. Most popular, I think, is crypto.js. So the arguments were an index, a previous hash, we creating the first block so there's no previous hash, some timestamp, and data. The first block is called the Genesis block. And upon creation of the block, we just calculate its hash and save it. So this is how like our super simple block works and how we calculate its hash. Now I would like to focus on the target. So there are two numbers, the difficulty and the target. The higher difficulty, the lower target is, because it will be harder and harder to find the lower number. The pad left is there to just show you the leading zeros. And this particular implementation of how we calculate the target is taken from algorithm that is called if hash. That's like crucial component of proof of work mining for Ethereum blockchain. So this number is like a magic number. It's just what my MacBook does in pretty reasonable time. All the, like, of course, it's JavaScript. It's not like the most. It's not the fastest implementation. So, but what you can see here. Oh, sorry. You can see here, for really small difficulty, the number is quite significant. There, we have a character at the beginning. So it means that it's a big number, basically. When we then increase the difficulty, the number is significantly lower. So you see those zeros at the beginning. So that's basically it. And all the magic between like calculating target from difficulty, really simple stuff. So now to the mining. The mining sounds quite advanced, but it's really simple. So we will accept the difficulty as a parameter to our block. Calculate the target, and that's our nonce that we are going to change over time. So while our numeric value of the hash from like the hash we've already computed and nonce, this value, this numeric value, has to be less than our target. And as long as it's greater or equal, we will increment the nonce. And that's what mining is. So we will try to mine a block. So here's our Genesis block once again. And as you can see here, the nonce is 0. When we try to mine it, it's going to increment. It's different each time because the variable here is timestamp. And now I've increased it a little bit too generously. So it takes significantly more time to do that. And there are blockchain implementations, like Bitcoin, for example, that aims to limit the number of transactions by design. The problem is that that's the distributed network, and to make it consistent, we sacrifice the throughput of the network. So when the miner solves the equation, solves the puzzle, then he has a right to commit transactions to the blockchain. And the incentive and how miners is choosing which transactions should be included. So the miners are incentivized by the transaction fee, and miner gets all transaction fee attached to every transaction. And there is a limited number of transactions that can get into the block. It depends on the implementation. In case of Bitcoin, it's like size of the block. In case of Ethereum, is the gas used by the block. So like computation, how complex computations are and memory usage of transactions. But no matter what it is, the miner is incentivized by his earnings based upon building a block. Okay, you've seen that one. So now when we can mine, we'll create a blockchain class. So the blockchain class will have a task of like storing all blocks, of course, and being able to validate the block. It will start with our Genesis block, and we could adjust difficulty through time to make certain blocks last, or mining certain block last for a certain time. In case of Bitcoin, it's something like 10 minutes per block. So when the network hash power, so how many hashes can network actually compute, is growing significantly, then the blockchain, the Bitcoin blockchain, will adjust the difficulty. So the first thing we validate when we want to say whether the block is valid, we will just check whether the previous hash of the block is matching actually the previous hash, just to make sure that it's coherent in terms of like the order of blocks in the blockchain. And then we will actually calculate the hash and compare. That's the entire proving whether the solution found by miner is correct. Now I'm trying to add like a second block to the blockchain. So the index is incremented, we add some data and reference the previous block by its hash. And you can see that without mining, the block should be invalid. So it's false. But when we try to mine it, then it's true. So that's basically it. I have one video. I didn't paste it here, totally by accident. So give me a second. No, it's not that. Okay, never mind. So when it comes to the Ethereum, and Ethereum is what I do for daily basis. Ethereum is a really interesting blockchain that actually allows you to run your program on it. So there are two types of accounts. One account is like a normal account that you control with your key, like which acts as a password. And the other type of account is a program, smart contract. We call it smart contract because the rules are embedded in the code. So everything that's going to happen on smart contracts, there is no other way to enforce it than by writing code. There is a certain danger to that because you cannot also upgrade it. So when you have a bug, you have a bug. Normal account is externally controlled by your private key, which you can think about it as your password. And smart contract is controlled as via its code. You can create a smart contract by writing in language called Solidity, compiling it, and then sending a transaction to a 0 address with the bytecode of that smart contract. And once you do that, it's possible to call the functions of the smart contract via other function calls. And I think this is where was the missing video. I had to change the order of slides. So what was missing is mining multiple blocks. So here we will try to mine 10 blocks. And we will implement an add block function for the blockchain. So it will check only whether the block is valid, the next block is valid, and then we'll push the block. In real implementation, we would also notify the network about the new block and populate the solution. And the mining of block with that difficulty is quite fast. So we will use performance hooks to just calculate how much time it took. And with that difficulty, it's going to be a single digit. And the solution is going to, it's average through all the blocks, but still it's going to depend on the timestamp. With bigger difficulty, it's going to change quite quickly. Let's skip that part. And it's going to mine those 10 blocks, but it will take over a minute. And back to the code. So that's the Solidity, which is a little bit Python, a little bit JavaScript, and types similar to C. So it's contract oriented, or at least that's what you can read in documentation. But think about contract as about class. So it's statically typed. It's like C-like typing. It's not scripting language. You have to compile it to the bytecode, and the bytecode is what runs on EVM, on Ethereum virtual machine, that every participant on the network is running. So imagine that when you submit a transaction to a smart contract, actually each node in the network that is a full node and executes all transactions and validates them is running your program and that particular function call. It's somehow similar to JavaScript. It's really easy for JavaScript developers to pick it up, especially if you have some experience with statically typed languages, or at least even with TypeScript. It relies heavily on JavaScript ecosystem. The most popular frameworks for Solidity are written in JavaScript. I'm talking about development frameworks, so what compiles your code, what you use to deploy your code, what you use to debug it and test it. Actually, tests are mostly written in JavaScript, and this is like integration level testing. We can write tests, unit tests in Solidity. A little bit. I think it defeats the point of unit tests, because unit tests should be fast to run, easy to write. It's not really necessary with Solidity, so the majority of projects sticks to writing tests in JavaScript. And the interesting part of the entire ecosystems are dApps. So dApps are those decentralized applications that use those smart contracts running on the blockchain as their backend. So you connect to Ethereum node. You can spin up your own Ethereum node and use it. There are also some public, but then you have to kind of trust it. Trust the organization that maintains this publicly available block. So I would suggest you run your own. You make calls via JSON RPC. It's quite low-level interface to calling smart contracts. So we use something like ethers.js, or in this example, web3.js, which is like an objective abstractions on top of JSON RPC. Using blockchain as a backend, and you have to support quite complex transaction lifecycle. So it's not simple as request, succeed, or failed. The lifecycle of a transaction can work two ways. Like, it can fail, of course, but it can also succeed and then disappear because there was chain reorganization. So it is possible that network will split the chain. So one part of the network is going to mine one chain, the other part of the network is going to mine different chain, because there was a situation in which two different nonces gave a solution. And now what part of the network will win? The more powerful. So the network that will be able to mine the next hash quicker, and the next and following hashes quicker, will win the race, and thus some transactions that were included only in the shorter chain will disappear. So you have to wait a certain time, and this time is expressed in the amount of blocks on top of your transaction to assume whether it's completed or not. So if you like Redux, if you like RxJS, and you work with web3.js, there are going to be interesting cases of undoing stuff in the UI. Most of applications just fail. So because this stuff is hard. But you can't fail when you do backend for it. So especially if you are interested in like writing backends, and you probably would like to write your backend in JavaScript because the best tooling for Ethereum is in JavaScript, there are going to be pretty interesting cases. If you would like to know more about JavaScript, that's like a free ebook. You can go grab it, and you'll get an email. The English version, sorry for that, because like it's really cool. There's the English-speaking person only. It costs money, but with WarsawJS it's like 50% off, so it will be like $4. And that's it. Thank you. If you have any questions.
Are there any questions? Any questions? Oh, there's one.
Hi, I just wanted to make sure which one of the books that you mentioned, the Polish one or the English one, is...
The Polish is free.
Okay, okay. And the other one costs how much?
For 50 with WarsawJS.
Right. Yeah, it's your book, and I just wanted to know which one is that. I will probably just have a look at that because your speech was interesting as well, and I wanted to dig it up.
Yeah, the ebook is. I didn't want to like get into promotion video. but like it's like 30 tips of some quirks that Solidity have because it's really badly designed language. It has a lot of quirks. It's like for me, it's like, oh, that's super awesome. We can learn them. There is like a game which I recommend you to try playing. It's called Eternaut or Eternaut, something like that. But you have to exploit like 10 or 15 smart contracts, basically hack them. They have like known bugs, and you have to find those bugs. After a certain time, it gets really hard. So like probably if you can like get through it without any additional help of like Stack Overflow or how to solve the 9th exercise on Ethernet, you are pretty good at writing smart contracts, and it shows that you understand the platform because there's a lot of quirks in platform like chain reorganization. It's like the smallest one. So the ebook is full of different quirks.
Okay, one more.
So just to make sure it's technically possible for you to mine something, and then all your work is undone because somebody has mined something further down the chain faster than you have.
Yes, exactly.
Okay.
It happens rarely. It's super rare to like get up to like 6 or 7 blocks that will going to disappear basically. But in Ethereum, for example, for this 12 to 13 seconds blockchain, which the block is every 12 or 13 seconds, it's safe to say that it's certain after 15 confirmations. That if you waited 15 blocks over the block that included your transaction, you are pretty good that no one is going to race you in that competition.
Blocks downwards would get erased then. If somebody
Yes, and something like that happened recently to Ethereum Classic, which is like a fork of Ethereum with less hash power. That's the danger of proof of work, that it can happen if there is because who's right in the proof of work mining? The majority by hash power is right. So if it happened that you have significantly more power than the rest of the network, then you can like change the history. But due to the but as long as it's more expensive to do that, to get such hash power than all assets represented by the cryptocurrency or the given state of the blockchain, it's like not feasible to do that. Like no one is going to spend $5 million to like get $500,000. And that's what happens. That's why attacks rarely happens on small blockchains that have like only the cryptocurrency that total cap may be worth only $500,000. But yeah, that's possible.
The last question, Piotr.
So I have a simple question. You focused mostly on proof of work, and what is your opinion on other consensus algorithms?
Oh, yeah, so like to give you some background, there are different ones. There's like proof of stake, delegated proof of stake. And proof of stake is, for example, I think it's really interesting. There is this richer get richer part in the proof of stake, but I think the proof of work isn't free of that because you can like you are richer just like buy more hardware. I think it's interesting. It's although I don't think it's proven at that scale, but like blockchain wasn't either 10 years ago, and for the last 10 years it's going pretty well in terms of like proof of work being unhackable, but it's like more safety by not being able. It's not like proven safety, of course. It's really hard to prove anything in cryptography, but we know a lot of smart people was working on it and wasn't able to break it. And it's really easy, as you could say, the simplest, the less hackable, let's say. And the proof of stake it's really interesting one, and the most talk about apart from proof of work. And it's like participants have certain amount of cryptocurrency, and they stake that cryptocurrency that, oh, that's like the right answer. That's are the right result of particular, that's the next block basically. And someone can, the network will challenge their answer with different people participating in the consensus, and majority wins. And everyone who says otherwise is losing or their stake. So if you're trying to cheat, you can lose all your stake. And the chance you're going to be chosen to answer the question, like what's the next state of the blockchain, is higher the higher stake you have. So it is kind of possible to cheat, but it's not feasible to do that. There is high chance that you will lose all your money. So in theory, it will work. Like if there is, I would say, if there is some system that is based on greed of people wanting to have more money than they have now, it's going to work. So that's what's at least proven for the last 10 years. So I'm not sure whether it answers your question. I hope at least partially. Thank you.